All right, so let's go to 12.2. Electrical circuits and components. Electrical circuits and components. Okay, so we'll call this part 1. Okay, so electrical circuits, we're talking electrical circuits. There are many, many components that goes into an electrical circuit. Does anybody tell me a few that they know of any components that go into an electrical circuit?
Wires.
Wires, okay, wires, what else?
Maybe some type of metal or something that makes up the circuit.
Okay, so that would kind of be the wires. Wires connect all the various components within a circuit, correct? Anybody else?
The outlet.
Outlet, okay, outlet, good. What else?
How about a switch?
Switch, good. A battery, maybe, a battery?
A light.
Light, okay, light. All right, what else? There is a resistor. Anybody heard the term resistor?
A capacitor.
Capacitor, there you go. Capacitor. Okay, so there are many different things that go in there, right? Each one of these things performs a different function within the circuit. Okay, all right. So wires, outlet, a switch, battery, light, resistor, capacitor. These are all good things. Okay, so let's talk about the resistor first. So then your resistor, okay. Basically, resistance is what? What are you resisting? What does a resistor resist? What does it block or try to block?
Electricity.
Well, yeah, the current flow, right? It tries to inhibit or kind of stop the current flowing, right? Okay, that's what it's called, a resistor. That's what it resists, okay? Resistor, okay? Resistors are measured in resistance, right? Resistance. And resistance is measured in ohms, okay? Measured in ohms, okay? If you go to page 407, there is a equation there where we have resistor is resistivity times the length divided by the cross-sectional area. Okay, so in other words, if I have current flowing through here, okay, and this is L, and the cross-section area here is A, and the resistivity is really nothing more than a unique characteristic of the material itself, right? So if you have something that resists it a lot, the resistivity will be high. And if it's low, this would be low, okay? All right. So what are some things that you would guess that have a low resistivity? These are things that you want to put in where you're connecting the components, right? In the wires, right? Because you do not want any line loss or losing anything that's happening between each component, correct? So something like copper or aluminum would have high or low resistivity. Lauren?
Yeah.
What do you think? Do you think the resistivity for copper is going to be high or low?
I would guess probably high.
Okay, so if it was high, would you want something like that in your wiring? Do you want to have a lot of loss in between components? Or would it be
No.
it would be the other way around, right? You would
Mhm.
want resistivity to actually be low. So actually the copper or aluminum would have low resistivity, whereas things like, I don't know, paper, wood, what are some other things that you use to insulate things, right? We call them insulation, right? What do you wrap around wire?
Is it rubber or something?
Yeah, that's sort of plastic, rubber, right? These type of things, right? These type of things are not going to conduct electrons back and forth. You want them to actually insulate it, so they would have a pretty high resistivity, right? So if you go to bottom of page 407, you can see that aluminum and copper have fairly low resistance, right? Whereas, what are some of the higher ones? Lead, okay, lead. Right. These are for most of the metals, right? These are all metals here. So that kind of stuff going on. Let's go ahead and flip the page. Ohm's law. So Ohm's law is really where we start. Ohm's law says that the book gives you V is equal to Ri. The traditional way is that we have this, where we have the current flowing is the voltage divided by the resistance, okay? It's the voltage divided by the resistance. So this would be voltage. This would be the resistance. This would be your current flow, okay? Where the voltage is measured in volts, resistance is still measured in ohms, current would be measured in amperes, okay? All right. So let's go ahead and look at that example there. Example, the electric resistance of a light bulb is 145 ohms. Determine the value of current flowing through the lamp when it is connected to a 120 volt source. So we have this guy, we're just going to plug it in here. And we're going to have 120 volts divided by 145 ohms. And if we do that, we would get 0.83 amps. Okay, all right. Notice, so you can, I mean, the book also said, book puts this as V is equal to IR. They're all the same, right? I is equal to, you know, I is equal to V over R, whatever you want to look at, however you want to look at it. Okay. So the American wire gauge. So this is how, when you start talking about the wiring, the wire gauge number basically tells you how thick or thin, or, you know, in diameter wise, what the wire looks like. Okay, so if you look at the page 409, there's a table 12.2 there. Okay. So if you look there, there's our wire gauge numbers starting from 0000 all the way through 40. Okay. So as the wire gauge number goes up, what's happening to the diameter?
Goes down.
Yeah, so the higher the wire gauge number, the thinner or the smaller the cross section is, because the diameter is smaller, right? So as the wire gauge number goes up, do you think it would have more resistance or less resistance? You would have more resistance, right? Because you're trying to shove the current through a smaller cross section, right? The larger the cross section, remember we had the resistance was equal to the resistivity, the larger the cross section here, right? So as the wire gauge number goes up, this guy is going to go up, which means that the resistivity is going to what? I mean, this is going to go down, right? It's going to go down. As the wire gauge number goes up, the cross-section area is going to go down, which means that the resistance will actually go up. Okay, all right. So that's that. I mean, obviously you don't have to memorize, I don't want you to memorize the diameter in mils and all that kind of stuff, but just know that as the wire gauge number gets higher and higher, you're looking at a smaller and smaller wire. Okay. So then we talk about electric power here. Okay, and they're going to give you the formula as P is equal to VI. Okay. Now, since we already know that I was V over R, right, this can be rewritten as V squared over R, right? Also, V was equal to IR, I squared R. Okay, so there's several derivative formulas that come out of this, right? Okay, so you can go like this, or like this, and they're all the same. Okay, they're all the same equation. They come from the same source there. All right, so now we have appliance and home electronics power consumption. Okay. So example 12.3, assuming that your electric power company is charging you 10 cents for each kilowatt hour usage, determine the cost of leaving 500-watt light bulbs on from 6 p.m. to until 11 p.m. Okay. So first of all, does anybody have a feel what a 100-watt light bulb means? Is that kind of bright or not so bright, or what is it? Anybody know?
It's pretty bright and very hot.
Yes, it is pretty bright and very hot, okay? 100 watts are basically, if you go to the light bulb section, they're gonna start from 40, and then they go to 60, and then they go to 100. So 40, 60, and 100 is basically your range where most people use for their home, okay? So if you go, 100 watts is gonna be the hottest, is gonna be the brightest. Okay, so we have 500-watt light bulbs that we're using from here to here. Okay, so how many hours? So we're looking at 5 hours of consumption, and each hour we are consuming how many watts? We'd be using 500 watts, right? Since there are 500-watt light bulbs, right? So it'll be 500 watts times 5 hours. So this is going to be 2500 watt hour, which is going to be equal to 2.5 kilowatt hour, right? And each kilowatt was going to be how many cents? Oh, we're going to do this 30 nights also. We're doing this 30 nights. So it's going to be 2.5 times 30 is going to be 75 kilowatt hours for a month. And each kilowatt was 10 cents. So that's going to be equate to what? $7.50, I guess, right? Yep, $7.50. Okay, so if you go to page 12 if you go to page 411, it kind of shows you how the range of power consumption, okay? If you look at the range of power consumption, what are the things that are gonna be really heavy hitters here?
Water heater.
Water heater. Water heater is like 4,500 to 5,500 kilowatts. I mean, that's kilowatts, right? That's watts. Okay, so it's gonna be 4.5 to 5.5 kilowatts. Okay, all right. So is there anything there that you thought was going to be pretty heavy hitter, but really isn't? Too bad they don't have air conditioning here. How about fans? Look at fans. Fans you would think would be a large hitter, but it's really not. Then you have stuff like hair dryer, right? Hair dry is a pretty big hitter there, like 1.2 to almost 2 kilowatts is your hair dryer, okay? So hair dryer is pretty big. Vacuum cleaner is pretty big. What else? Wow. Clothes washer is pretty small considering what it does. 350 to 500. Okay. That's about, I don't know, what's that equivalent? That's almost half of a coffee maker. So if you look at it that way, washer is pretty energy efficient, right? Okay. All right, let's go ahead and flip the page and we will come to series and parallel circuits, okay? So I want you guys to kind of briefly read through the series and parallel circuits. Jot some notes down and then we'll talk about it in the second half.